Welcome back to Control System Lectures. Now I have several videos right now on the root locus, both on how to plot it and also how to use it to design systems. So I thought it'd be nice to go through the comment section of those videos and then answer some of the more common questions that I receive here in a video format, rather than try to explain it in words as a reply. And then hopefully I can clear up some of the confusion. So let's get to the first question. I was asked, why do we start calling the poles of a transfer function the roots, like we do here in a root locus? Well, a system transfer function is made up of two polynomials, one in the numerator and one in the denominator. And the polynomial in the denominator is called the characteristic equation because it characterizes the stability of the system. If the polynomial in the numerator is equal to 0 for some value of s, then the entire transfer function equals 0, and that value of s is called a 0. If the polynomial in the denominator is equal to 0, then there's a divide by 0 and the transfer function blows up to infinity, and that value of s is called a pole. Okay, so now we understand the poles and the zeros of a transfer function. And to solve for them, we're setting the polynomials equal to 0 and then solving for what's called the roots of the polynomial, or the solutions. So zeros are the roots of the numerator, and poles are the roots of the characteristic equation, or the denominator. And those roots are what we're plotting in the root locus. So in this case, roots of the characteristic equation and the poles of the system are the exact same thing. And due to laziness inherent in language, we just shorten down to roots and poles. It's confusing because we don't usually call zeros the roots of the numerator, and I actually don't know why we don't refer to the root locus as the pole locus. But unfortunately, swapping roots and poles is just something we do now, and if you're confused by the term that someone else is using, it's best to ask for clarification rather than making an assumption of what they mean by it. Okay, for the second question, I was asked how to plot the damping ratio line on a root locus plot with just overshoot given as 15%. Let me just start with the equation because it's really easy to calculate. You can go from percent overshoot in the time domain to damping ratio in the s domain with this equation, and then you can convert the damping ratio zeta into an angle beta by taking the inverse cosine of it. Beta is the angle off the real axis in the s-plane off the negative real axis. So that if you draw a straight line from the origin at that angle, all points along that line have the exact same damping ratio. And we can visualize this equation in action by plotting it in Matlab. Okay, the first thing we should do is define our percent overshoot variable, PO, and we'll set it to 15%. And then we'll use that percent overshoot to solve for zeta using the equation that I wrote earlier. One thing in Matlab that might confuse you if you're not used to it is that the natural log, which is normally ln, is just written out as log, and it's the function log 10 if you want to use the base 10 logarithm. Alright, so we found our damping ratio zeta to be just over 0.5, and now I want to define a second order transfer function. And since natural frequency, which I'm giving the variable w, doesn't impact overshoot, I'm free to choose any value. I'll assign it randomly just 1 radians per second just to make it easy. Now, to create a transfer function object in Matlab, you can use the function tf and define the numerator and denominator, or you can use a function like zpk where you define zeros, poles, and gain. And there's a few other methods as well. But I find it's easier just to create s as a transfer function object first, and then I can use it like a variable in an equation to create more complicated transfer functions. Here I've generated a second order transfer function using my calculated zeta and my chosen natural frequency. Okay, cool, so that's what it looks like. And now we can see what the step response looks like for this transfer function. Perfect. And here you can see that the step response starts at 0, and as we expected, there is some amount of overshoot. And if I zoom in on just this part, you can see that there is indeed exactly 15% overshoot. Let's go back to the command window and verify that the natural frequency really doesn't impact the overshoot for a second order system. I'll loop through 4 different frequencies, 0.5, 1, 1.5, and 2 radians per second. I'll recalculate the transfer function and plot the step response on the same graph over and over again. And here's what that looks like. It's a similar story as before. All 4 responses have exactly 15% overshoot, and just the rise time and settling time was affected by the change in natural frequency. Lastly, let's see how the poles are actually moving through the S-plane as I loop through those 4 frequencies. To do that, I'm using a function called PZMap, which stands for pole zero mapping, and like the name suggests, it just plots the poles and zeros in the S-plane. And here are the poles for the 4 different frequencies, all in a straight line from the origin, just as we were expecting. So that's just the quick demonstration to show that the equation works. To answer this question fully, I need to go on a long and wandering story, so I hope you stay with me for it. If you have a system described by a second-order transfer function, and you apply a step input to it, then it might have a response in the time domain that looks something like this. And that looks similar to what we saw in the Matlab plot. But if you wanted to describe the performance of this response, you could say, well, it starts at 0 and then goes up kind of fast and then squiggles back and forth a bit around 1. Or to be a little more accurate, you could describe the performance of this response with metrics like the time it takes to rise, the time of its peak value, the time it takes to settle, its overshoot expressed as a percentage, and its steady state error. And sometimes you'll get design requirements expressed as one or more of these performance measures. And what you are designing to depends on what is important for the system that you're building. For example, a telescope drive system might really care about having 0 steady state error, but not care so much about the amount of time it takes to slew the telescope, which is rise time, or the overshoot that happens while it's settling. Whereas a system that needs to heat a liquid with a gas burner might not tolerate any temperature overshoot because of possible damage to the liquid in the tank. These are the time domain requirements of the system, and are typically the easiest to understand since we experience the world in the time domain. But we can also define performance with frequency domain and S-domain requirements. Now, I've covered the frequency domain pretty well in my videos on Bode and Nyquist plots, the sensitivity function, and stability margins. And since this is a root locus video, I want to focus on the S-domain requirements, which means where we want to place the locations of the poles and zeros in the S-domain. And the trick is trying to figure out how we express all of these requirements in all 3 of these different domains. But before we talk about that, let's talk about how we define the locations of the poles and zeros. We can define them in rectangular coordinates as the real and imaginary component, or we can define them in polar coordinates as the damping ratio and the natural frequency, where again the damping ratio is related to that angle of the line off the negative real axis. So at this point, the question you might have though is, why give requirements in the S-domain at all? I mean, as long as the system behaves as you want in the time domain, who cares where the poles and zeros are? Why don't we just stick with our requirements in the time domain only? And the answer is because we have tools at our disposal for analyzing systems and designing controllers in the S-domain that don't exist in the time domain, and a root locus plot is one of those. So in order to take advantage of these powerful design tools, we need to find a way to describe system requirements in the S-domain. Otherwise, if we wanted to use the root locus plot, we'd have to design a controller, and then convert it back to the time domain to see the results, and then go back to the S-domain and make changes, and then go back to the time domain. You could see how this would be inefficient. So let's see how we actually express our time domain requirements as pole and zero locations in the S-plane. And here's where the confusion can set in if you don't know exactly why you're doing this. The very ideas of damping ratio and natural frequency are only defined for a second-order system. You can see them right there in the second-order equation. Now you can always use damping ratio and natural frequency to define a physical location in the S-plane in the polar coordinates, but they lose their meaning if the system is not a second-order system, or at least behaves like a second-order system. In control theory, we have this obsession with second-order systems, because you can build up higher orders from them, and many real systems exhibit second-order behavior, so they're worth studying. But just remember that in our percent overshoot problem, if I hadn't defined the system as second order, or if the system didn't have a pair of dominant poles that made it behave like a second order, then the relationship between percent overshoot and damping would not have held. So when you're defining requirements for your system, you can't just say, I want a system with damping ratio of 0.5, without first knowing that your system behaves like a second order. Otherwise, you're just defining nonsense. For example, if you have these 5 poles in your system, what's the damping ratio? Is it the one on the real axis? Is it the close pair? Is it the far pair? Do you average them all together? And then after you come up with some answer, could you use that to calculate the percent overshoot? You should play around with these higher order systems and see what you think. At the risk of confusing you, I do want to say one other thing. You can usually define the time and frequency domain requirements for higher order systems. For example, rise time still makes sense even if the system response to a step input looks something like this. So the bottom line is that even though you have an equation that converts percent overshoot to damping ratio, you still need to know when it makes sense to use it. Okay, thanks for sticking around for that long answer. And let's move on to the next question. I was asked if the damping ratio is the cosine of beta, how can damping ratio be more than 1 without multiplying the cosine of beta with some constant? Well, this is a good opportunity to work through the math for why damping ratio equals the cosine of beta to begin with. As I hammered on in the last question, it's important that we start with a second order system. From here, we're concerned with damping ratio and how it affects the poles of the system. We can set the characteristic equation to 0, and then use the quadratic equation to solve for the roots. I'll plug in the a, b, and c, and then simplify the equation down to this one that I've written in white. You can pause the video at this point right here if you want to check the work and let it sink in a bit. But at this point, we can make an assumption that zeta is less than 1. If that's the case, then zeta squared minus 1 is negative, and causes the term under the square root to be imaginary. I find it's easier to factor out the minus 1 explicitly, and then pull the imaginary term j out, just so we can see the real and imaginary components clearly. There are 2 roots, and both have the same real component but opposite signs on the imaginary component. If we just plot one of them, we can see that it's at negative omega naught zeta in the real axis, and positive omega naught times the square root of 1 minus zeta squared in the imaginary axis. Now it should be easier to see that if we hold zeta constant, the pole scales with omega naught along that line that intersects with the origin. But what is the angle of that line? This can be determined using trigonometry and recognizing the right triangle that is made with the real axis. The adjacent side of the triangle is omega naught times zeta, and the hypotenuse is the square root of the real and imaginary component. And I really love these types of problems, because as you expand it all out, all of the terms cancel and you're left with just cosine of beta equals zeta. Okay, but we made a fundamental assumption here when calculating this equation. Namely, we assumed that zeta was less than 1. We did that right here. So when we say that damping ratio is the inverse cosine of zeta, that only holds for zeta equals 0 to 1. Let's see what happens when zeta is greater than 1. If zeta is greater than 1, then the 2 poles separate and exist on the real axis. So rather than a complex pair, we now have 2 first-order real poles. So I guess this is the long way of saying that all of these helpful equations have assumptions that were made when creating them. So it's important that you understand where they came from and when you can use them, and not just to blindly calculate answers. I hope this helped. Okay, moving on to question number 4. I was asked, how do I solve for the gain required to place the roots where I want them using the root locus plot? Now, I mentioned in one of my videos that I don't really like calculating gain from hand-drawn root locus plots, because I don't feel that's the best use of them. I personally think root locus is fantastic for understanding how the poles move as you manipulate the system gain, or adding additional poles and zeros. But I think calculating the gain in most cases requires a very accurate plot, and that defeats the purpose of doing a rough sketch by hand. But I understand people like the thrill of hand calculating and the rush you get from manipulating those numbers, so I won't deny them the chance to do it. Recall that we start with a feedback system that looks like this, with proportional gain k and open loop system g of s. I will arbitrarily choose g of s to have a pole at -4 and one at -2, mainly because I need a second order system to meet the requirements I'm about to give. But the technique I'm about to explain will work for higher order systems as well. The root locus for g of s exists between -2 and -4 on the real line, and then the two poles crash into each other and leave the real axis at positive and negative 90 degrees. Now let's use the root locus to determine what value of k will give us a 15% overshoot for our closed loop system. And recall from earlier that for this second order system, that means that zeta needs to be just over about 0.5, and that gives us a beta angle of about 1 radian. And if I draw my line of constant damping, I can see where it crosses the root locus, and know that we want our two poles to end up right where they cross. And again, we can solve for where this is using trigonometry. This triangle has a real component of 3, and an imaginary component equal to 3 times the tangent of beta. I found it to be just under 5. So we know precisely where the poles should be, and not just approximately now from a crude drawing. Recall from the introduction to root locus, the closed loop transfer function is g of s divided by 1 plus k times g of s. And if we set the characteristic equation to 0, we can solve for the closed loop poles. But we have our closed loop poles. We just solved for them. So now we can work backwards by setting s in the characteristic equation to one of our poles. I'm using minus 3 plus 4.97j for this example, but you could have chosen the negative one too. Now the only unknown in this equation is the gain k, which we can solve for, and we get 5.14. So the general steps to solve for gain is to first draw your root locus, figure out where you want to place the pole, and then plug that into your closed loop characteristic equation and just solve for k. Now with more complicated plots, it gets harder to solve for the exact location of the pole, but for simple ones like I just did, it's pretty straightforward. So the last question I get often is, could I show the way to draw root locus plots in Matlab? And the answer is yes, I can and I definitely want to, but not in this video because I want to spend more than just a few minutes doing it. But I promise the very next video will cover plotting root locus in detail in Matlab. If you have even more questions or comments, please leave them below and I will try to answer them. Don't forget to subscribe so you don't miss any future videos, and thanks for watching.